There are things in the universe that we can measure with remarkable precision. And yet, we still don't understand what they are. Not because we lack data, but because the data doesn't fit. Over the past few decades, as our instruments have improved, something unexpected has happened. The more clearly we observe the universe, the more often it refuses to behave the way we expect. These are not theories, not speculation. These are real observations, things we have seen, recorded, and verified. And they don't quite make sense. So tonight, we are going to explore some of the strangest phenomena ever observed in space and what they might be trying to tell us. Let me start with something that happened on August 15th, 1977. A man named Jerry Emmon was reviewing data from the Big Ear radio telescope at Ohio State University. The telescope was part of SETI, the search for extraterrestrial intelligence. Every day, it scanned the sky, listening for radio signals that might indicate intelligent life somewhere out there. Most days, the data was boring, just background noise from space. Nothing unusual. But on this particular day, Emmon noticed something that made him grab a red pen and write a single word in the margin of the printout. Wow. That moment is why we now call it the wow signal. The signal lasted just 72 seconds. That might not sound like much, but in radio astronomy, that is an unusually long, clean detection. During that brief window, it was about 30 times stronger than the normal background noise. Not a subtle fluctuation, but a clear, isolated spike. Imagine scanning through static, and suddenly, for just over a minute, a single precise tone rises above everything else, then disappears completely, and never returns. The signal's frequency was around 1,420 megahertz. That frequency sits very close to something called the hydrogen line, a natural radio frequency produced by hydrogen atoms. Why does that matter? Because hydrogen is the most common element in the universe. If an alien civilization wanted to send a signal that other civilizations might recognize, choosing a frequency connected to hydrogen would make a lot of sense. It would be like choosing a universal language, based on something every civilization studying the universe would eventually discover. Now here is another curious detail. The Big Ear telescope had two receivers that scanned the same region of the sky, one after the other. The second receiver would observe the same patch of sky about 3 minutes later. But the signal only appeared in the first receiver. It never showed up in the second. That tells us something important. The signal must have lasted less than 3 minutes. And based on the data we have, it was probably close to 72 seconds. Since 1977, astronomers have returned to that exact location in the sky many times. They have used more powerful telescopes, listened at the same frequency and nearby frequencies, and searched carefully for any sign that the signal might appear again, but they found nothing. The wow signal was a one-time event. Now, let me be clear about the uncertainty here. The signal could have been artificial or natural. The Big Ear telescope couldn't pinpoint locations precisely. So, we know the general direction, but not the specific source. Some scientists have proposed natural explanations. Maybe it was a signal from a passing comet. Comets can emit radio waves when the solar wind interacts with their hydrogen clouds. In 2016, a researcher named Antonio Parra suggested that two comets, known as 266P Christensen and P208Y2, were in that region of space at the time. But there's a problem with the comet theory. The signal was incredibly narrow-band. It occupied a very specific frequency. Most natural sources tend to produce signals spread across a broader range of frequencies. But the narrowness of the wow signal is much more consistent with something artificial. Something deliberately transmitting on a chosen frequency. Because of that, Some scientists have wondered whether the signal might have come from an intelligent source. Other researchers have suggested a different explanation. They argue it might have been interference from Earth. Perhaps a satellite, an aircraft, or some ground-based transmitter that happened to send a signal at exactly the right time. However, there is a problem with that idea. The Big Ear telescope was specifically designed to filter out terrestrial interference, and the signal appeared to come from a direction in space that did not match any known satellite or aircraft operating at that time. So, what was it? Honestly, it remains unexplained. And that is exactly what makes it so fascinating. Nearly 50 years later, the WOW signal remains one of the most intriguing unexplained observations in the history of SETI. The search for extraterrestrial intelligence. The fact that it never repeated is both frustrating and significant. If it really came from an alien civilization, why would they transmit only once? One possibility is something scientists sometimes call a lighthouse strategy. Imagine a powerful signal sweeping across the galaxy like the beam of a lighthouse rotating across the ocean. In that case, we might have caught the signal for only a brief moment as the beam passed across Earth. Or perhaps it was a one-time broadcast. Maybe it was never meant for us at all. It could have been an accidental spillover from some other communication between distant civilizations. But there is another possibility. Maybe it was not aliens at all. The universe is full of natural processes that produce radio waves. Pulsars, quasars, magnetars, supernova remnants. Astronomers are constantly discovering new types of cosmic radio sources. So the WOW signal might have been a natural phenomenon that we simply did not understand at the time. Something we have never seen before, and perhaps never seen again. The truth is, we may never know. The signal lasted 72 seconds in 1977, and it never returned. A brief moment in human history, captured in a line of data and a single handwritten word. It is a mystery frozen in time, and at the same time, a reminder of how much about the universe still remains unexplained. Somewhere out there in the direction of Sagittarius, something sent out a powerful narrow-band radio signal, and we happen to catch it. That's either the most incredible coincidence in the history of astronomy, or it's evidence of something extraordinary. Either way, it's strange, and it's why almost 5 decades later, people are still talking about the WOW signal. Now let us talk about something that is happening right now. A star that has been driving astronomers crazy since 2011. Its official name is KIC 8462852, but most people call it Tabby's star. Named after astronomer Tabetha Boyajian, who led the research team studying it. Tabby's star sits about 1,460 light-years away from Earth in the constellation Cygnus. At first glance, it looks like a completely ordinary star. It is slightly larger and hotter than our Sun. Nothing about it should make it special. But in 2011, the Kepler Space Telescope noticed something strange. Stars do dim sometimes. That part is normal. If a planet passes in front of a star from our point of view, the star's light drops slightly. That is actually how we detect exoplanets. For example, if Earth passed in front of the Sun as seen from another star system, the Sun's brightness would drop by about 0.01%. It is tiny, but still measurable. A much larger planet like Jupiter would cause the Sun to dim by about 1% if it crossed in front of it. That is the kind of dimming astronomers expect from planets. Small, regular, and predictable. But Tabby's star does not behave that way. In 2011, its brightness suddenly dropped by about 15%. Then the light returned. In 2013, the brightness dropped again, this time by about 22%. Then it recovered once more. Even stranger. These dimming events were irregular. They did not repeat on predictable schedules, and they lasted different amounts of time. Sometimes the star would dim only a little. Other times, the dimming was dramatic. At its most extreme, the brightness dropped by about 22%. That is enormous. A planet the size of Jupiter would only block about 1% of a star's light. To block 22%, you would need something far larger than any planet. Something absolutely massive. Possibly something comparable in scale to the star itself. When the discovery was first announced, it triggered a wave of speculation among astronomers. What could possibly be blocking that much light? And this is where the story became even more interesting. By this point, astronomers were running out of familiar explanations. The dimming was too deep, too irregular, and too inconsistent with anything we had seen before. When standard models fail, science does not stop. It widens the range of possibilities. One of those possibilities was unconventional. What if the dimming wasn't caused by natural objects at all? What if something was actively altering the star's light? This is where the idea of a Dyson swarm enters the conversation, not as a conclusion, but as a theoretical possibility. If something like that existed, it could block different amounts of starlight as the structures moved through orbit. And from far away, the star's brightness might appear to drop in irregular and unpredictable ways. It would be irregular. It would dim the star by large amounts. It would look exactly like what we were seeing with Tabby's star. Now, before you get too excited, let me be clear. Most astronomers don't think Tabby's star is an alien megastructure. The alien hypothesis was always the least likely explanation. But here's the thing. We had to consider it because we couldn't explain the observations any other way. That's how weird this star is. So, if it's not aliens, what is it? Scientists proposed several natural explanations. Maybe there's a giant swarm of comets orbiting the star. If a family of comets passed in front of the star, they would block light irregularly. Their dust tails would create uneven dimming. This was a leading theory for a while. But there are problems with the comet theory. Where did all these comets come from? You'd need an enormous number of them to block 22% of the star's light. And comets would produce dust, which would make the star appear redder when it's dimmed. Tabby's star doesn't do that. The color stays the same even when it's dimmed. Another theory suggested maybe there was a recent collision. If two large objects smash together near the star, the debris cloud could block light irregularly as it spreads out. But again, we'd expect to see excess infrared radiation from warm dust. We don't see that. Some scientists suggested the dimming might be caused by the star itself. Maybe it's a variable star that dims naturally. But Tabby's star doesn't show the characteristics of known variable stars, and the dimming pattern is too irregular. Then in 2017, astronomers made another observation. They caught Tabby's star dimming again and observed it across multiple wavelengths of light. What they found was interesting. The dimming was more pronounced in blue light than in red light. That's consistent with dust blocking the starlight. Small dust particles scatter blue light more effectively than red light. It's the same reason Earth's sky is blue. So maybe it is dust after all. But if it's dust, where's it coming from? Why is there so much of it? Why is the pattern so irregular? The latest observations suggest that Tabby's star might have a large debris field around it. Perhaps from a destroyed planet or a massive collision or some other catastrophic event. The debris blocks light irregularly as it orbits. This is the current leading explanation. But it's not fully satisfying. The full picture remains unclear. And here's what makes this even stranger. Tabby's star is still doing it. We've now watched this star for more than a decade. It keeps dimming in weird, unpredictable ways. We have multiple datasets from different telescopes. The phenomenon is real. It's not a measurement error. It's not a glitch. Something is actually blocking the light from this star in ways that remain puzzling. As of 2025, Tabby's star remains one of the strangest objects in the sky. Out of hundreds of billions of stars, this is the only one that behaves like this. We've never seen anything else quite like it. Maybe one day we'll figure it out. Maybe we'll discover it's a natural process we just haven't encountered before. Or maybe, just maybe, it's something else entirely. Something we haven't even thought of yet. Let me tell you about something scientists discovered in 2019 that absolutely should not exist. They are called odd radio circles, often shortened to ORCs. The name is actually perfect. They are odd. They are circles, and we can only see them in radio wavelengths. Here is what astronomers noticed. If you point a radio telescope towards certain parts of the sky, you sometimes see a perfect circular ring of radio emission. The circle is enormous, often hundreds of thousands of light years across. And here is the strange part. At the center of many of these circles, there is a galaxy. The first of these mysterious structures was discovered by a team led by astronomer Ray Norris. They were using the Australian Square Kilometre Array Pathfinder, often called ASCAP, a powerful radio telescope designed to survey large areas of the sky. ASCAP observes the universe in radio waves, which means it reveals structures that optical telescopes simply cannot see. When the research team began processing their data, they noticed these strange circular patterns. At first, they assumed it was a data processing error, because in astronomy, perfect circles are suspicious. Nature rarely produces geometric shapes that precise. But when they checked the data carefully, the circles were real. They found 3 more. Then other telescopes confirmed them. As of 2025, we found about a dozen orcs. They're rare. They're large, and their origin remains a puzzle. Let me describe what we're seeing. Each OC is a ring or shell of radio emission. The structure appears as a near-perfect circle in some cases, almost geometrically precise. And that alone is unusual. But the real surprise comes when we consider the scale. These rings can span hundreds of thousands to over 1 million light-years across, large enough to contain entire galaxy groups. So we are not just looking at a shape. We are looking at something vast and unexpectedly ordered. Some of them stretch more than 1 million light-years across. That is about 10 times the diameter of the Milky Way. These are truly massive cosmic structures. Astronomers do sometimes see circular shapes in the sky. For example, supernova remnants can appear roughly circular. These are expanding shells of debris left behind after a star explodes. But supernova remnants are much smaller, and they are usually associated with relatively recent stellar explosions. The odd radio circles, or ORCs, are far too large and far too distant to be supernova remnants. Another possibility could be planetary nebulae. These are shells of gas expelled by dying stars near the end of their lives. Planetary nebulae can also appear circular, but once again, they are much smaller, and they are found inside our own galaxy. The ORCs are clearly not planetary nebulae. Some galaxies also produce radio lobes, where jets from a central black hole shoot streams of matter far into space. In some cases, those structures can appear circular depending on the viewing angle. However, the ORCs do not match the typical properties of radio galaxies. The galaxies at their centers do not appear to host the extremely active supermassive black holes that would normally create such enormous radio structures. So, what exactly are they? The honest answer is, we do not know. Scientists have proposed several theories, but none of them has fully explained what we are seeing. Maybe they're shock waves from massive explosions in the center of galaxies. If a galaxy went through a period of intense star formation, or if its central black hole suddenly became active, It could create a blast wave that expands outward. Over millions of years, this wave could create a spherical shell of radio emission. But if that's the case, why don't we see more of them galaxies go through active phases all the time? We should see these structures more often. Another theory suggests they might be related to merging galaxies. When two galaxies collide, all sorts of crazy things happen. Maybe the collision creates shock waves that expand outward as spherical shells. But there is a problem with that explanation. Galaxy mergers are common. ORCs are extremely rare. Because of that, some scientists have suggested even more exotic possibilities. Perhaps these circles are the imprints of primordial events that happened in the early universe. Some have even wondered whether they could be connected to cosmic strings or some other unusual feature of space-time. These ideas are fascinating, but they remain highly speculative. The truth is that astronomers are still in the discovery phase when it comes to odd radio circles, or ORCs. We have only known about them for a few years. To understand them properly, scientists need many more observations. They need to find additional examples and study the galaxies at their centers in much greater detail. What makes ORCs especially fascinating is that they represent something entirely new. Astronomers have been studying the radio sky for decades. But ORCs only appeared once we began using more sensitive radio telescopes. In other words, these structures were probably always there. We simply did not have instruments powerful enough to detect them until recently. And that reveals something important about astronomy. The universe is full of phenomena that we have not yet discovered. Not because they are hiding from us, but because we have not yet built the tools capable of seeing them. Every time we develop a better telescope, or observe the universe in a new wavelength of light, something unexpected appears. ORCs are a perfect example of this. Nobody predicted them. Nobody was searching for giant radio circles around distant galaxies. They appeared as a complete surprise. And now astronomers are trying to understand what they are, how they formed, and what they might reveal about the deeper workings of the universe. As of 2025, ORCs, or odd radio circles, remain unexplained. We know they exist. We know roughly what they look like, but we still do not understand what causes them. Strange structures are appearing in the radio sky, and they are waiting for someone to finally figure them out. Now let us move to something that challenges the rules on an even larger scale. In 2021 and 2024, astronomers discovered two enormous cosmic structures that challenge one of the fundamental principles of cosmology. The first structure is called the Giant Arc. It was discovered by Alexia Lopez, a doctoral student at the University of Central Lancashire. The Giant Arc is an immense structure made of galaxies that stretches about 3.3 billion light-years across. That number does not describe how far away it is. That number describes how large the structure itself is. In other words, light would need 3.3 billion years to travel from one end of the structure to the other. To put that into perspective, the entire observable universe is estimated to be about 93 billion light-years across. So this single structure represents a significant fraction of the scale of the observable cosmos. The Giant Arc itself lies roughly 9.2 billion light-years away from Earth. When astronomers map its galaxies, they appear arranged in a vast curving arc, almost like a gigantic cosmic bow across the sky. That unusual shape is what gave the structure its name. Then, in 2024, the same research team discovered another enormous structure in nearly the same region of the sky. They call it the Big Ring. This structure is also immense, measuring about 1.3 billion light-years in diameter. It is located at roughly the same distance from Earth, about 9.2 billion light-years away. And here is where the story becomes even more intriguing. Both of these enormous structures exist in the same region of the sky and at roughly the same cosmic distance. In other words, Astronomers are seeing two gigantic structures in the same part of the universe. And that is a little suspicious. It suggests they might be related somehow. Now, why is this a problem? Let me explain. In cosmology, there's something called the cosmological principle. This principle states that when you look at the universe on large enough scales, it should be roughly uniform. No matter which direction you look, you should see roughly the same density of matter. The universe should be homogeneous and isotropic at large scales. This principle is fundamental to our understanding of the universe. It's built into the standard model of cosmology. It's supported by observations of the cosmic microwave background, which shows that the early universe was remarkably uniform. But the giant arc and the big ring challenge this principle. They appear to be too large. According to calculations based on the standard cosmological model, cosmic structures should not be able to grow larger than about 1.2 billion light-years across. That limit comes from our understanding of how gravity has had time to pull matter together since the Big Bang. But the giant arc is nearly 3 times larger than that theoretical limit. Even the Big Ring, at about 1.3 billion light-years in diameter, is already pushing the boundary. If these structures are real, and current observations strongly suggest that they are, then one of two things must be true. Either our theoretical limit is wrong, or something unusual is happening in the universe. It could mean that the cosmological principle does not hold as well as we once believed. Maybe the universe is lumpier than our models predict. Or perhaps there are cosmic processes we still do not understand that can create structures far larger than theory allows. Of course, some astronomers have questioned whether these structures are truly real. When scientists study the large-scale distribution of galaxies, it is possible to see patterns that are not actually there. The human brain is very good at finding connections. You might see a line or arc of galaxies that appears meaningful, when in reality it is simply a coincidence. But Alexia Lopez and her team performed careful statistical analysis. Their results suggest that the probability of the giant arc being a random alignment is about 1 in 6,000. That is a very small probability, which means the structure most likely is real. The Big Ring statistics are even more compelling, and the fact that both structures are in the same region of space makes a coincidence less likely. So what are they? One possibility is that they're related to something called baryon acoustic oscillations. In the early universe, sound waves traveled through the hot plasma. These waves left an imprint on how matter is distributed. They create a preferred scale, a characteristic size for structures. But the giant arc and the big ring don't match the expected size from baryon acoustic oscillations. They're much larger. Another possibility is that they're related to cosmic strings. These are hypothetical one-dimensional defects in space-time, predicted by some theories but never observed. If cosmic strings exist, they could create large-scale structures as galaxies form preferentially along them. But cosmic strings are speculative. We have no direct evidence they exist. The most troubling possibility is that our cosmological model is incomplete. Maybe the cosmological principle isn't as robust as we thought. Maybe the universe has large-scale structure that we didn't account for. Maybe at the largest scales, things are more complex than our models predict. This wouldn't mean the Big Bang theory is wrong. It would mean we need to refine our understanding of how structure formed in the universe. That's how science works. You make observations, build models, and when observations don't match models, you update the models. As of 2025, the giant arc and the big ring remain controversial. Some astronomers are convinced they're real structures that challenge the cosmological principle. Others are more skeptical, thinking they might be statistical anomalies or misinterpretations of the data. What's clear is that the universe at the larger scales is more complex than we thought. And these enormous structures, whether they turn out to be real anomalies or something else, are pushing us to think harder about how the cosmos is organized. Let me tell you about a place in the universe that is almost empty. It is called the Boötes Void, and it is one of the strangest features in the large-scale structure of the cosmos. The Boötes Void is a region of space about 330 million light-years across. To put that into perspective, that is more than 3,000 times the diameter of the Milky Way. It is an enormous volume of space. And here is what makes it so strange. A region this large should normally contain about 2,000 galaxies. That estimate comes from the average density of galaxies observed throughout the universe. But when astronomers survey the Boötes Void, they find only about 60 galaxies. Everything else is missing. The region is not completely empty. There are still a few dozen galaxies scattered throughout it. But compared with what should be there, it is remarkably devoid of matter. That is why astronomers call it a cosmic void. The Boötes Void was discovered in 1981 by astronomer Robert Kirshner and his colleagues. They were mapping the large-scale distribution of galaxies when they noticed an enormous empty region located in the constellation Boötes. Initially, they weren't sure if it was real or just an artifact of their survey. Maybe they had missed some galaxies. Maybe their detection methods weren't working properly in that region. But follow-up observations confirmed it. The void is real. There really is a huge bubble of space with almost no galaxies in it. Now, cosmic voids themselves are not unusual in the universe. The cosmic web I mentioned earlier is made of long filaments of galaxies surrounding vast empty regions called voids. Most voids are tens of millions of light-years across. They are fairly common features in the large-scale structure of the cosmos. But the Boötes Void is different. It is much larger than typical voids, and is considered one of the largest known supervoids in the nearby universe. Because of its enormous size, its existence raises important questions about how cosmic structure formed. Here is the key idea. The universe began in a state that was almost perfectly uniform. Observations of the cosmic microwave background show that about 380,000 years after the Big Bang, matter was distributed almost evenly throughout space. There were tiny differences in density, but those variations were incredibly small. Over billions of years, gravity amplified those tiny differences. Regions that were slightly denser attracted more matter and gradually grew into galaxies, stars, and filaments. Meanwhile, regions that were slightly less dense slowly lost matter to their surroundings and expanded into cosmic voids. Computer simulations of this process reproduce the cosmic web that astronomers observe today. Filaments, galaxy clusters, and large voids all emerge naturally when gravity acts on those original density variations. But the simulations also predict limits. Voids can only grow to a certain size given the age of the universe and the strength of gravitational interactions. And the Boötes Void sits very close to that theoretical limit, at roughly 330 million light-years across. It is about as large as cosmic voids are expected to become. That makes it particularly interesting. It represents an extreme example of how structure forms in the universe, and it pushes our theoretical models to their limits. If our models are correct, we should not see voids much larger than the Boötes Void. If we ever discover voids significantly bigger than this, it would suggest that something in our current models of cosmic structure might be wrong. So far, the Boötes Void still fits within the theoretical limits predicted by cosmology, but it sits very close to that boundary. And that alone makes it an important object for astronomers to study carefully. There is another fascinating aspect of the Boötes Void. The few galaxies that exist inside it are often unusual. Some of them are forming stars at surprisingly high rates. Others have strange shapes or unexpected properties. It almost seems as if the extreme isolation of the void has influenced how these galaxies evolved. Think about what life is like for a galaxy. If you are located in a dense region of space, you are constantly interacting with other galaxies. Gravitational forces pull on you, Sometimes galaxies collide and merge. Gas can be exchanged. You are part of a crowded and dynamic environment. But if you are a galaxy inside the Boötes Void, the situation is very different. You are almost completely alone. Your nearest neighbor might be millions of light years away. You evolve in near isolation, without the gravitational disturbances that galaxies in crowded regions experience. That isolation could change how a galaxy evolves. Perhaps galaxies in voids keep more of their gas because nothing nearby strips it away. Perhaps their star formation follows a different path, over billions of years. That isolation might produce galaxies with unusual characteristics. In that sense, the galaxies inside the Boötes Void give astronomers a rare opportunity. They allow us to study what happens to galaxies when they evolve in cosmic solitude. It's a natural experiment that the universe has set up for us. But the fundamental question remains: why is the Boötes Void so empty? Why did this particular region of space end up with so few galaxies? The answer probably goes back to the initial conditions of the universe. This region must have started out with a slightly lower density than average, over billions of years. Gravity pulled matter out of the region toward denser areas, creating the void we see today. But why was this region less dense to begin with? That's a deeper question. It relates to whatever process created the initial density variations in the very early universe. Most cosmologists think these variations came from quantum fluctuations during the inflationary epoch, a brief period of exponential expansion right after the Big Bang. These quantum fluctuations were random. Some regions ended up slightly denser, some slightly less dense. Most variations were small, but occasionally by chance you'd get a larger variation. The Boötes Void might be the result of one of those slightly larger variations in the initial conditions of the universe. It is remarkable when you think about it. The emptiness we see in the Boötes Void today, stretching about 330 million light-years across, may have originated as a tiny quantum fluctuation during the first fraction of a second after the Big Bang. That microscopic difference was gradually amplified by gravity over 13.8 billion years, eventually becoming the enormous supervoid we observe today. The universe can be strange in that way. The smallest variations can produce the largest consequences, given enough time. And speaking of the early universe, let me tell you about one of the most puzzling features ever discovered in the cosmic microwave background. It is called the CMB Cold Spot, and it has been puzzling cosmologists since 2003. The cosmic microwave background, often abbreviated as the CMB, is the faint afterglow of the Big Bang. When the universe was about 380,000 years old, it cooled enough for electrons and protons to combine, forming neutral hydrogen atoms. Before that moment, the universe was essentially opaque. Photons could not travel very far before colliding with free electrons. But once neutral atoms formed, the universe suddenly became transparent. Light was finally able to travel freely through space. The cosmic microwave background is made of those ancient photons. They have been traveling through the universe for about 13.8 billion years. And today, we detect them as a faint microwave glow coming from every direction in the sky. The remarkable thing about the cosmic microwave background, or CMB, is how incredibly uniform it is. If you measure its temperature in different directions across the sky, it is almost exactly the same everywhere. The average temperature is about 2.725 Kelvin, just a few degrees above absolute zero. But when astronomers measure the CMB very carefully, they notice tiny variations. Some regions are slightly warmer, others are slightly cooler. These temperature differences are extremely small, only about 1 part in 100,000. Yet these tiny fluctuations are incredibly important. They represent the imprints of density variations in the early universe. Regions that were slightly denser ended up appearing slightly cooler in the CMB map. over billions of years. Those denser regions eventually grew into the galaxies and galaxy clusters we see today. That is why the cosmic microwave background is such an important scientific tool. It is essentially a snapshot of the universe when it was only about 380,000 years old. By studying the pattern of hot and cold spots across the CMB, scientists can learn about the initial conditions of the cosmos. Space missions such as COBE, WMAP, and Planck have mapped the cosmic microwave background in extraordinary detail. And when scientists carefully analyzed those maps, they discovered something unexpected. There is a region of the sky, roughly 10 degrees across, that appears significantly cooler than scientists expected. This feature is known as the CMB Cold Spot. It is not just slightly cooler, it is about 70 millionths of a degree colder than the average CMB temperature. That might sound incredibly small, but in the context of the tiny fluctuations in the CMB, it is actually a very large anomaly. The cold spot is located in the constellation Eridanus. The cold spot has an oval shape, spanning roughly 10 degrees by 5 degrees across the sky. That is enormous when viewed from Earth. In fact, it appears about 50 times larger than the apparent size of the full moon. Here is why it is so unusual. Using the standard model of cosmology, scientists can estimate how likely it is for such a large cold region to appear purely by chance in the cosmic microwave background. The probability is about 2%. That does not mean it is impossible, but it does mean it is unlikely. A probability of 2% means that if we could simulate the universe 100 different times, each starting with random initial conditions, we would expect to see a cold spot like this in only about 2 of those universes. But we only observe one universe. So either we happen to live in one of those rare cases, or there may be something physically unusual behind the cold spot. Scientists have proposed several possible explanations. One idea is that the cold spot might be caused by an enormous supervoid. Remember that cosmic voids are regions of space containing very few galaxies. If there were an extremely large void located between us and the cosmic microwave background in that direction, photons passing through the region could lose a small amount of energy. This effect is known as the integrated Sachs-Wolf effect. As the photons travel through a vast, underdense region of space, the gravitational environment slightly alters their energy, making them appear a little cooler when we observe them in the CMB map. Here's how it works. As photons enter a void, they climb out of a gravitational well, losing energy. As they leave the void, they fall into a gravitational well, gaining energy. If the universe weren't expanding, these effects would cancel out. But because the universe is expanding, the void gets larger and less dense while the photons are crossing it. This means the photons gain less energy on the way out of the region than they lost when they entered it. The net result is simple. The photons end up slightly cooler. So in theory, a large supervoid located between us and the cosmic microwave background could create a cold spot in the CMB. And astronomers have indeed found evidence of a large void in the direction of the cold spot. It is not nearly as large as the Boötes Void, but it is still a substantial region of low galaxy density. But here is the problem. Even when scientists include that void in their calculations, it can only explain a small fraction of the cold spot's temperature difference. To fully explain the effect, we would need an extremely large void, far larger than anything astronomers have actually observed in that region of space. And so far, we have not found evidence for a void large enough to produce the entire anomaly. Because of that, scientists have proposed other explanations. One of the more exotic possibilities is that the cold spot might be related to a collision between our universe and another universe. In some versions of cosmic inflation theory, our universe may be only one bubble inside a vast cosmic foam of many universes, sometimes called the multiverse. If another universe bubble collided with ours in the early moments after the Big Bang, that collision could leave a detectable imprint in the cosmic microwave background. Such a collision might appear as a large circular region that is either slightly colder or slightly warmer than the surrounding universe. This is a very exotic explanation, and there is no direct evidence for it beyond the cold spot itself. But the fact that scientists even consider ideas like a collision between universes shows just how puzzling this anomaly is. The more conventional explanations simply do not seem to work perfectly. A third possibility is that the cold spot is simply a statistical fluke. A probability of about 2% means the event is rare, but not impossible. Maybe we just happen to live in a universe where this unlikely feature exists. After all, rare things do happen. The real challenge is that we only have one cosmic microwave background to observe. We cannot repeat the experiment. We cannot create 100 universes and see how many of them produce cold spots. We have only one data point: the universe we live in. That makes it very difficult to determine whether the cold spot represents a meaningful anomaly or simply a coincidence. If we had 10 universes to observe, and 9 of them showed no cold spot, then we could confidently say the feature in our universe was truly unusual. But we do not have that luxury. As of 2025, the CMB Cold Spot remains unexplained. It might be partly caused by a supervoid, but that explanation does not seem to account for the entire effect. It might simply be a statistical fluctuation, although many scientists find that explanation unsatisfying. Or it might hint at some form of exotic physics, though that possibility remains highly speculative. What is clear is that the cold spot is anomalous. It stands out in maps of the cosmic microwave background. It is larger and colder than our models predict. And until scientists find a convincing explanation, it remains one of the strange features of our universe that we do not yet fully understand. Now let us move to something even stranger. A star that appears to break the rules of nuclear physics. Or at least seems to. It is called Przybylski's star, officially designated HD 101065. This unusual star lies about 370 light-years away in the constellation Centaurus. From a distance, Przybylski's star looks fairly ordinary. It is an A-type star, roughly twice the mass of our Sun and about 6 times more luminous. At first glance, nothing seems unusual, but when astronomers analyzed its light spectrum, they discovered something truly bizarre. The star contains elements that should not exist in any star for more than a few weeks. Specifically, it contains technetium, promethium, and other radioactive elements with short half-lives. Let me explain why this is a problem. Stars create elements through nuclear fusion. In their cores, hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. In the most massive stars, the process continues, creating heavier and heavier elements up to iron. Elements heavier than iron are created in supernova explosions and other energetic events. When a massive star explodes, the incredible pressures and temperatures create these heavy elements. They're scattered into space where they can be incorporated into new stars. So when we see heavy elements in a star's atmosphere, we assume they were there when the star formed. The star was born from a cloud of gas that contained material from previous generations of stars, including their heavy elements. But here's the catch. Some heavy elements are radioactive. They decay over time. Uranium, for example, has a half-life of about 4.5 billion years. That means half of any uranium will decay into lighter elements in about 4.5 billion years. But even after billions of years, some uranium can still remain. Technetium, on the other hand, has no stable isotopes. All forms of technetium are radioactive. The longest-lived isotope, Technetium-98 has a half-life of about 4.2 million years. That is extremely short on cosmic timescales. Przybylski's star is probably several billion years old. Based on its characteristics, it appears to be a mature star rather than a young one. If the star formed with technetium in its atmosphere, that technetium should have decayed billions of years ago. There should be none left. Yet when astronomers analyze the star's spectrum, they see clear evidence of technetium. They also detect promethium, another radioactive element with a short half-life. And these elements have been observed consistently since the star was first studied in detail in the 1960s. So the question is simple. Where is this technetium coming from? There are a few possible explanations, but none of them are completely satisfying. One idea is that the star may be creating technetium on its surface through some unknown nuclear process. Maybe there's a mechanism we don't understand that can produce these elements in the star's atmosphere. But this seems unlikely. We have a pretty good understanding of nuclear physics, and there's no known process that could do this in the cool outer layers of a star. Another idea is that the technetium is being brought up from the star's interior. Maybe deep inside the star, nuclear reactions are creating technetium, and convection currents are carrying it to the surface. But again, this doesn't quite work. The star's interior isn't hot enough to create technetium through normal nuclear reactions. A third idea, which sounds like science fiction, is that the star contains super-heavy elements. Elements with atomic numbers far beyond anything we've seen. In theoretical nuclear physics, there's something called the island of stability. The idea is that if you go far enough up the periodic table beyond the known elements, you might find a region where certain super-heavy elements are relatively stable. Some of these super-heavy elements, if they exist, might decay into technetium or promethium as intermediate products. So the star might contain super-heavy elements that are slowly decaying, replenishing the supply of technetium and promethium. This idea is highly speculative. We have never observed super-heavy elements occurring naturally. Scientists have created a few of them in particle accelerators, but they decay almost instantly. The so-called island of stability is a theoretical prediction, not an established fact. Still, Przybylski's star is so unusual that astronomers are willing to consider exotic explanations. Another strange thing about the star is its chemical composition. It contains unusually high amounts of certain rare earth elements. Its spectrum shows strong lines from elements such as holmium, dysprosium, and europium. These elements are far more abundant in Przybylski's star than they are in the Sun. Because of this, it is classified as a chemically peculiar star. There are several types of chemically peculiar stars, and they are thought to form because of atmospheric processes that concentrate certain elements. Radiation pressure and magnetic fields can cause some elements to sink or rise within a star's atmosphere, creating unusual abundance patterns. But even among chemically peculiar stars, Przybylski's star is exceptional. Its abundance patterns are more extreme than almost any other known star, and the presence of short-lived radioactive elements makes it unique. Some astronomers have wondered if Przybylski's star might have a companion. Maybe it is part of a binary system with a neutron star or a white dwarf. And material from the companion could be falling onto Przybylski's star, bringing radioactive elements with it. But so far, astronomers see no evidence of a companion. The star's motion does not show the wobble we would expect if it had an orbiting partner. As of 2025, Przybylski's star remains a mystery. For more than 60 years, astronomers have been observing it. And for more than 60 years, its spectrum has continued to show technetium and promethium. These elements should have decayed away long ago, yet they are still present. Either there is a nuclear process we do not yet understand, or the star contains some form of exotic matter. Or there is something fundamentally wrong with our observations or interpretations. None of these possibilities is particularly satisfying, which is why Przybylski's star remains one of the strangest objects in the sky. On October 19th, 2017, astronomers using the Pan-STARRS telescope in Hawaii detected something moving through the solar system. At first, they thought it was a comet or asteroid. But as more data came in, they realized the object was very different. They named it Oumuamua, a Hawaiian word meaning scout or messenger. It became the first confirmed interstellar object ever observed passing through our solar system. Oumuamua came from outside the solar system, from interstellar space. It approached from the direction of the constellation Lyra, passed through the inner solar system, and then continued on its way back into interstellar space. We only had a few weeks to study it before it became too faint and distant to observe. What astronomers learned during those weeks was both fascinating and confusing. Oumuamua was strange. Really strange. First, its shape. Based on how its brightness changed as it tumbled through space, astronomers calculated that Oumuamua was extremely elongated. The best estimates suggested it was about 400 meters long and only about 40 meters wide. That is a ratio of roughly 10 to 1. It may have been cigar-shaped, or possibly more like a pancake, depending on the exact geometry. This is unusual. Most asteroids and comets tend to be more spherical or irregular, not extremely long and thin. An elongated shape like Oumuamua is possible, but it is rare. Second, its surface. Oumuamua appeared reddish in color, similar to some objects found in the outer solar system. This suggests that its surface had been exposed to cosmic radiation for a long time, which can slowly darken and redden surface material. In non diste desaf, so far. That part was not especially surprising. But Oumuamua showed no signs of a coma. When comets approach the sun, the heat causes ice on their surface to vaporize. This creates a cloud of gas and dust called a coma, which gives comets their familiar glowing appearance. Oumuamua showed no coma at all. Even when it passed close to the sun, well inside the orbit of Mercury, no coma appeared. This suggested that it was not a typical comet. Perhaps it was more like an asteroid, made mostly of rock or metal. But then came the really strange part. Oumuamua's trajectory did not behave exactly as expected. After it passed the sun and began leaving the solar system, it was accelerating slightly more than gravity alone could explain. When you calculate an object's trajectory, you account for the gravitational pull of the sun and the planets. Those forces are predictable. Based on gravity alone, astronomers can predict exactly where Oumuamua should be at any given time. But the object was moving slightly faster than expected. Something other than gravity appeared to be pushing it. For comets, this is normal. When ice on a comet vaporizes, the escaping gas produces a rocket effect, pushing the comet slightly. This type of non-gravitational acceleration is well understood. But Oumuamua did not show a coma. So what was pushing it? Scientists proposed several possibilities. Maybe Oumuamua was outgassing, but the gas was not carrying enough dust to produce a visible coma. Maybe gas was escaping mostly from one side, creating a small thrust that we simply could not detect clearly. Some observations suggested there might have been very faint traces of gas, but the evidence was uncertain. Another idea was that Oumuamua was being pushed by sunlight. All objects in the solar system experience radiation pressure from the sun. Photons from the sun strike an object and transfer a tiny amount of momentum, pushing it slightly. For most objects, this force is extremely small, far weaker than gravity. But if an object is very thin and very light, like a sheet or sail, radiation pressure can become significant. Perhaps Oumuamua was extremely thin. Maybe it was more like a pancake than a cigar. If it were only a few meters thick but hundreds of meters wide and made of relatively light material, then radiation pressure might explain the observed acceleration. But this raises another question. How would such an object form naturally? Why would it be so thin? It is difficult to imagine natural processes producing a rigid sheet of rock or ice hundreds of meters across but only a few meters thick. And this is where the discussion becomes much more speculative. In 2018, two Harvard astronomers, Abraham Loeb and Shmuel Bialy, published a paper suggesting that Oumuamua might be artificial. Specifically, they proposed that it could be a light sail, a thin reflective sheet designed to be pushed by starlight. Such a sail could function as a spacecraft or a probe sent by an advanced alien civilization. This suggestion generated a great deal of controversy. Most scientists were skeptical. In astronomy, the alien hypothesis is usually considered the last resort. You only invoke extraterrestrial technology after every natural explanation has been exhausted. And in the case of Oumuamua, there were still natural explanations, even if some of them seemed somewhat strained. Loeb argued that the possibility should at least be considered if Oumuamua were artificial. It would represent one of the most important discoveries in human history. The fact that something is unlikely does not mean it should be dismissed without examination. Still, most astronomers believe that Oumuamua is natural, probably a comet with unusual properties, an asteroid with an unusual shape, or perhaps a fragment of a shattered planet from another star system. These explanations require far fewer assumptions than the alien hypothesis. The real problem is that we may never know for certain. Oumuamua is now far away from the Sun, moving back into interstellar space. It has become too faint and too distant to observe with current telescopes. We only had a few weeks to study it. And during that time, we did not gather all the data scientists would have liked. If another interstellar object enters the solar system in the future, astronomers will be much better prepared to observe it. We'll have more telescopes ready to observe the next one, and we'll be able to collect much more detailed data. In fact, a second interstellar object was discovered in 2019. It is called Borisov, and it is clearly a comet. Borisov has a coma, a tail, and it behaves almost exactly like comets in our own solar system. In many ways, Borisov is unremarkable, and that is what makes it remarkable. It shows that interstellar comets can be very similar to the comets we already know, but Oumuamua remains unique. We have never seen another object quite like it. Maybe it was simply an unusual natural object. Maybe it was something more mysterious. The truth is that we will probably never know for certain. What we do know is that interstellar objects pass through our solar system from time to time. The galaxy is full of asteroids and comets that have been ejected from their home star systems. They drift through interstellar space. Some of them by chance pass through our solar system. We can detect them now. And everyone we detect teaches us something new about the universe beyond our Sunday. In June of 2018, telescopes around the world detected a bright explosion in a galaxy 200 million light-years away. They labeled it at 2018 Cow. The name comes from the automated naming system for astronomical transients. The cow part is just random letters, but it's become the nickname for this event. At first, astronomers thought it was a supernova. Supernova are exploding stars, and they happen regularly. We detect dozens of them every year. But as they gathered more data, they realized that 2018 Cow was different. Very different. First, it was extremely bright, about 10 to 100 times brighter than a typical supernova, and it got bright fast. Most supernovae take weeks to reach peak brightness. At 2018, Cow reached peak brightness in just a few days. Then it faded quickly. Most supernovae remained visible for months, gradually fading over time. At 2018, Cow faded in weeks. It was like someone turned on a cosmic flashlight, shined it for a brief moment, and turned it off again. The light spectrum was also unusual. It did not match the spectra of any known types of supernovae. The temperatures were extremely high, tens of thousands of degrees, and the explosion appeared to be expanding very rapidly, at a significant fraction of the speed of light. Astronomers were baffled. What kind of explosion could be this bright, this fast, this hot, and so different from anything they had seen before? They quickly realized AT2018 Cow was not alone. As astronomers searched through archival data and continued monitoring the sky, they began to find more events like it. These ultra-fast, ultra-bright transients appeared to represent an entirely new class of astronomical event. They are sometimes called fast blue optical transients, or FBOTs. The name describes them well. They brighten extremely quickly and then fade again in days or weeks, far faster than most other cosmic explosions. They are blue, meaning they emit large amounts of ultraviolet light, which indicates extremely high temperatures. They are also optical transients, meaning they appear and disappear in visible light. As of 2025, astronomers have found only a small number of these events, perhaps a few dozen. They appear to be rare, or at least rarely detected, and scientists still do not fully understand what causes them. Several theories have been proposed. One idea is that these events mark the birth of black holes or neutron stars. When a massive star dies, its core collapses. If the core is heavy enough, it forms a black hole. If it is lighter, it forms a neutron star. This collapse releases an enormous amount of energy. Normally, most of that energy goes into blowing apart the outer layers of the star, producing a supernova. But in some cases, the energy might be released in a different way. It might produce a jet that punches through the star's outer layers and shoots into space. Such a jet could create a bright, fast transient that looks very different from a normal supernova. Another idea is that FBOTs are caused by a star being torn apart by a black hole. This process is known as tidal disruption. If a star passes too close to a black hole, the intense gravitational forces stretch and tear the star apart. The stellar material then spirals inward toward the black hole, heating up and releasing enormous amounts of energy. Tidal disruption events are known to occur, and they can be extremely bright. However, most of them evolve much more slowly than FBOTs. They usually take months to reach peak brightness and fade. FBOTs evolve much faster. One possibility is that FBOTs are a special type of tidal disruption event, perhaps involving a small black hole destroying a white dwarf or neutron star. The dynamics in such a case would be very different, which could help explain the extreme speed and brightness of these events. A third possibility involves interactions between two compact objects. For example, a white dwarf might collide with another white dwarf, or even with a neutron star. Such a collision would release an enormous amount of energy in a very short time, potentially producing an FBOT. The truth is that we still do not know. FBOTs are such a recent discovery that astronomers are still trying to understand their basic properties. Every new detection provides more data, allowing scientists to gradually narrow down the possible explanations. What makes FBOTs particularly exciting is that they appear to represent something genuinely new. Astronomy has been studying supernovae for centuries, but events like these show that the universe can still surprise us with phenomena we have never seen before. We've developed detailed models of how different types of supernova work, We thought we understood exploding stars pretty well. Then along comes at 2018 Cow and it breaks all the rules. It's brighter, faster, and different from anything we expected. It forced astronomers to realize there are types of cosmic explosions they hadn't anticipated. This happens sometimes in science. You think you understand something, and then nature throws you a curveball. You detect something that simply does not fit your models. That is when science becomes truly interesting. Because it means there is something new to learn. As telescopes continue to improve and astronomers monitor more of the sky more frequently, we will probably detect more FBOTs. And each one will provide additional clues. Over time, scientists will likely figure out what causes them. But right now, in 2025, they remain one of the strange and unexplained phenomena in the universe. Now let me tell you about a star that, in some ways, should not exist. Its official designation is HD 140283, but astronomers often call it the Methuselah star, named after the biblical figure who supposedly lived for 969 years. The nickname reflects the star's extraordinary age. The Methuselah star is located about 190 light-years from Earth. It can actually be seen with binoculars, if you know where to look. In the constellation Libra, it is an old star, classified as a subgiant, meaning it has exhausted the hydrogen in its core and is beginning to evolve away from the main sequence. Stars in this stage are typically very ancient. They formed in the early universe when conditions were different from today. By studying them, we can learn about the universe's history. Astronomers can estimate a star's age using several methods. One method looks at the star's composition. The universe started with almost pure hydrogen and helium. Over time, stars have created heavier elements through nuclear fusion and supernova explosions. These heavy elements, which astronomers call metals, accumulate over time. So, a star with very few metals probably formed very early, before many generations of stars had enriched the interstellar medium with heavy elements. The Methuselah star has extremely low metallicity. It contains about 250 times less iron than the Sun, suggesting that it formed during the very early history of the universe. This suggests it formed early, when the universe was young and heavy. Elements were rare. Another method to estimate age looks at the star's nuclear fuel consumption. Stars fuse hydrogen into helium in their cores. Once they run out of hydrogen, they start fusing helium into heavier elements. The rate of these reactions depends on the star's mass and composition. By observing a star's properties, its temperature, luminosity, and composition, astronomers can estimate how long it has been burning and therefore how old it is. When scientists applied these methods to the Methuselah star, they obtained an uncomfortable result. The star's age appeared to be around 14 billion years, with error bars that overlapped uncomfortably with the age of the universe itself. Here is the problem. The universe is only about 13.8 billion years old. We know this from several independent measurements. The cosmic microwave background, the expansion rate of the universe, and the ages of the oldest star clusters all point to an age of roughly 13.8 billion years. So, how could a star appear to be around 14 billion years old in a universe that is only 13.8 billion years old? The error bars technically allow the star to be just slightly younger than the universe, but the margin is extremely small. It is uncomfortably close. When this result was first published, some scientists wondered whether our estimate of the universe's age might be wrong. Perhaps the universe was actually older than we thought. But as measurements improved over time, the age of the universe became increasingly certain. It is very close to 13.8 billion years, with only small uncertainties. That means the problem must lie in the star's age estimate. But how could that be? The methods astronomers use to estimate stellar ages are well established and have been tested across many different types of stars. These estimates are based on solid physics. The key issue lies in the error bars. The Methuselah star's age is estimated to be around 14 billion years. But with uncertainties that technically allow it to be as young as 13.7 or 13.8 billion years. That would place it just barely younger than the universe itself. The margin is extremely tight. But it remains technically possible. If the star formed very soon after the Big Bang, within the first few 100 million years, then it could indeed be that old. But even this scenario feels uncomfortable. The very first stars in the universe were very different from the stars we see today. They formed from pure hydrogen and helium, with virtually no heavy elements. Those first-generation stars were probably very massive and short-lived. The Methuselah star does not match the expected profile of one of those first-generation stars. Instead, it contains a small amount of heavy elements. Astronomers call these elements metals, and their presence suggests the star belongs to the second generation of stars. Second-generation stars form from gas that has already been enriched by the supernova explosions of earlier stars. But second-generation stars could not have formed immediately after the Big Bang. The first stars had to live out their short lives, explode as supernovae, and enrich the interstellar medium with heavier elements. That process would take hundreds of millions of years. So the Methuselah star probably formed at least a few 100 million years after the Big Bang. If that is true, then its maximum possible age would be roughly 13.5 billion years or less. The difficulty is that observations sometimes continue to suggest an age slightly older than that, which is why the Methuselah star remains one of the most puzzling objects astronomers have studied. Even with improved measurements and refined models, the star's age estimate stays around 14 billion years. The error bars have gotten smaller over time, which is the opposite of what we'd hope. We'd like the error bars to encompass a younger age that's comfortable. So, what's going on? There are a few possibilities. One is that our models of stellar evolution are wrong in some subtle way. Maybe low metallicity stars evolve differently than we think. Maybe there's a process we don't understand that affects their nuclear burning rates. Another possibility is that our distance measurement to the star is wrong. Age estimates depend on knowing the stars. Luminosity and luminosity estimates depend on knowing the distance. If the star is closer or farther than we think, its age estimate would change. Astronomers have measured the distance to the Methuselah star using parallax. As Earth orbits the Sun, nearby stars appear to shift position against the background of more distant stars. By measuring this shift, you can calculate the distance. The Gaia satellite has measured parallaxes for billions of stars with unprecedented precision, including the Methuselah star. But there's still some uncertainty. Maybe the distance is slightly different than we think, enough to bring the age estimate down to something more comfortable. A third possibility is that the star is simply younger than our best estimates suggest, and we are just seeing the unlucky end of the statistical distribution. When scientists measure something with uncertainty, the true value can sometimes lie near the edge of the error bars. Perhaps the Methuselah star is actually around 13.5 billion years old, and the 14.5 billion year estimate is simply a statistical fluctuation. As of 2025, the Methuselah star remains uncomfortably old. Astronomers continue refining their measurements, hoping to resolve this tension. For now, however, it remains one of the strangest objects in the universe, a star that, according to our best measurements, appears to be almost as old as the universe itself. Of course, it cannot truly be older than the universe. Something in our measurements or models must be slightly off. The challenge is figuring out exactly what that is, and that process takes time. Until scientists resolve the issue, the Methuselah star will continue to puzzle astronomers. Now here is something worth considering. At first glance, all of these discoveries seem unrelated. A radio signal from the 1970s. A star that dims without pattern. Vast structures that shouldn't exist. Regions of space that are almost completely empty. Each one feels like an isolated mystery. But when we step back, a different pattern begins to emerge. Again and again. We are encountering observations that don't quite fit our expectations. Not dramatically wrong, but subtly. Persistently inconsistent. And that raises a deeper question. Not about any one phenomenon, but about whether our current understanding of the universe is simply incomplete. That the universe is more complex than our current models suggest. That there are processes, phenomena, or physics we don't fully understand yet. Think about it. The WOW signal tells us there are radio sources we haven't identified. Tabby star tells us stars can behave in unexpected ways. Odd radio circles tell us that galaxies can create enormous structures we are only beginning to detect. The giant arc and the big ring suggest that the universe may not be as perfectly uniform as we once believed. And the Boötes Void shows us that cosmic emptiness can be far more extreme than many of our models predicted. Each of these mysteries on its own might seem like just an oddity, something unusual that scientists need to explain. But when we look at them together, they begin to form a broader picture, a picture of a universe that continues to surprise us, revealing phenomena we never expected to see. This is actually quite normal in the history of science. When we reach the edge of understanding something new, we often begin to notice anomalies, observations that do not quite fit within our existing theories. At first, they seem like isolated problems, but eventually, someone connects the dots. Someone realizes these anomalies are all symptoms of something bigger, something we haven't understood yet. That's how we discovered relativity. In the late 1800s, there were several problems in physics. The orbit of Mercury didn't quite match predictions. The speed of light seemed to be constant, regardless of how you measured it. These seemed like separate issues. Then Einstein came along and showed they were both explained by the same new theory. Relativity connected the dots. Maybe that's what's happening now with these cosmic mysteries. Maybe they're all pieces of a puzzle. And someday, someone will figure out how they fit together. They'll develop a new theory or discover a new phenomenon that explains all of them at once. Or maybe not. Maybe each mystery has its own separate explanation. Maybe the WOW signal was a comet. Maybe Tabby star has a dust cloud. Maybe odd radio circles are shockwaves. Maybe the giant arc is simply a statistical coincidence. Maybe Przybylski's star is powered by some unknown nuclear process that we have not yet discovered. At this stage, we simply do not know. These mysteries will only be resolved when scientists gather more data and develop better models to explain them. But there is another intriguing possibility that some of these anomalies might be connected. That they are all hinting at something deeper about how the universe works. That possibility is what makes this such an exciting time to study astronomy. Let me tell you something that might surprise you. Some of the greatest advances in astronomy came from being wrong. From making observations that contradicted what we thought we knew. In the early 1900s, astronomers observed distant galaxies and noticed they were moving away from us. The farther away they were, the faster they were receding. This didn't make sense. Why would everything be moving away from us? Are we at the center of the universe? But as they thought about it more, they realized this pattern would happen if the universe itself was expanding. If space itself was stretching, then galaxies would move apart, and the ones that are farther away would appear to move faster. This observation led to the Big Bang theory. The entire universe started from a single point and has been expanding ever since. Nobody expected that. It contradicted the prevailing view that the universe was static and unchanging. But the observations forced astronomers to change their minds. And that unexpected observation became the foundation of modern cosmology. In the 1960s, astronomers discovered quasars. These were points of light that looked like stars but had very strange properties. They were incredibly bright, sometimes brighter than entire galaxies. And they were extremely far away, billions of light years from Earth. Nothing scientists knew about normal stars could explain how such objects could shine with that much energy. Eventually, astronomers realized that quasars were not stars at all. They were actually the centers of distant galaxies, each containing a supermassive black hole. As matter falls toward these black holes, enormous amounts of energy are released, creating some of the brightest sustained sources of light in the universe. This discovery completely changed how scientists thought about galaxies. Astronomers came to understand that most large galaxies contain supermassive black holes at their centers, and that these black holes play an important role in galaxy evolution. None of this was widely understood before the discovery of quasars forced scientists to reconsider what might be possible. Then, in the 1980s, astronomers studying the expansion of the universe expected to find that the expansion was slowing down. Gravity from all the matter in the universe should be pulling everything back together, gradually slowing the expansion of space. But when astronomers made careful measurements using distant supernovae, they discovered the opposite. The expansion of the universe was actually accelerating. This result made no sense at first. What could possibly be pushing the universe apart? That observation eventually led scientists to propose the idea of dark energy, a mysterious form of energy that appears to make up about 68% of the universe's total energy. Even today, we still do not fully understand what dark energy actually is. But we know it must exist because the observations demand it. Each of these discoveries began with something that did not make sense. An observation that contradicted expectations. And each time, instead of ignoring the data or assuming it must be wrong, astronomers chose to follow where the evidence led. They changed their theories to match reality. That's what's happening now with the mysteries I've described. We have observations that don't fit our current understanding. We could ignore them. We could assume they're measurement errors or statistical flukes. But that's not how science works. Instead, we take them seriously. We study them carefully. We try to understand them. And maybe, just maybe, they'll lead to the next big breakthrough in our understanding of the universe. The reason we're finding so many strange things in space right now isn't because the universe suddenly got stranger. It's because our tools got better. We can see things we couldn't see before. We can measure things we couldn't measure before. Think about the WOW signal. It was detected by a radio telescope in 1977. That telescope, the Big Ear, was relatively simple by today's standards. It could detect strong radio signals, but it couldn't pinpoint their exact location very well. It couldn't analyze the signals in great detail. Today we have much better radio telescopes. The Very Large Array in New Mexico, the ALMA Array in Chile, the upcoming Square Kilometer Array, which will be the most sensitive radio telescope ever built. These instruments can detect much fainter signals. They can locate sources precisely. They can analyze signals in incredible detail. If the WOW signal happened today, we'd learn so much more about it. We'd know exactly where it came from. We'd know its properties much more precisely. We might even be able to figure out what caused it. The same is true for all these mysteries. We're finding them because we have better tools. And as our tools continue to improve, we'll find more. We'll also understand the ones we've already found much better. Tabby's star was discovered by the Kepler Space Telescope, which launched in 2009. Kepler was designed to find exoplanets by watching for the tiny dips in starlight when planets pass in front of their stars. It monitored more than 150 000 stars continuously for several years. Before Kepler, we couldn't do this kind of monitoring. We had to observe each star individually, and we couldn't watch them continuously. Tabby's star's weird dimming pattern would have been nearly impossible to detect. But Kepler gave us continuous data on thousands of stars, and that's how we found Tabby's star. We were not even looking for these things at first. We were actually searching for planets. But the Kepler Space Telescope, with its ability to monitor stars continuously for long periods of time, revealed phenomena that nobody expected. Now we have TESS, the Transiting Exoplanet Survey Satellite, which is continuing similar work by scanning the sky for planets orbiting distant stars. We also have the James Webb Space Telescope, capable of observing the universe in infrared light with extraordinary sensitivity. On Earth, astronomers now operate ground-based telescopes equipped with adaptive optics, allowing them to see with a clarity that approaches what space telescopes can achieve. Each of these instruments opens a new window into the universe. And the more ways we observe the cosmos, the more unexpected discoveries we tend to make. In the coming years, astronomers will have even more powerful tools. The extremely large telescope is currently being built in Chile. When it is completed, it will have a mirror about 39 meters across, an enormous size by astronomical standards. With that capability, it will be able to observe objects that are incredibly faint and extremely distant. It will also allow scientists to analyze the atmospheres of exoplanets, searching for possible signs of life beyond our solar system. The square kilometer array, when complete, will have a collecting area of 1 square kilometer. That's about 250 acres of radio receivers. It will be 50 times more sensitive than any current radio telescope. If there are radio signals out there like the WOW signal, the square kilometer array will find them. NASA is planning new space telescopes. Some will look for signs of life on exoplanets. Some will study the early universe. Some will map out dark matter. Each will have the potential to discover something unexpected. And here's the thing. Every time we build a better telescope, we find surprises. Every single time. There's never been a case where we built a more sensitive instrument and found exactly what we expected and nothing more. The universe always surprises us. So, we can be pretty confident that in the coming decades, we'll discover more strange things, more mysteries to puzzle over, more observations that don't quite fit our theories. And that's exciting because mysteries drive progress. They force us to think harder, to question our assumptions, to develop new ideas. Let me tell you something about the people who study these mysteries. They're not some distant group of super intelligent beings who have everything figured out. They're regular people. Science is driven by curious people who get excited when they find something strange. People who stay up late trying to understand confusing data. And people who argue with each other about what observations really mean. When Jerry Amon saw the WOW signal in 1977, he was reviewing paper printouts of radio telescope data. The Big Ear telescope recorded its observations on paper, with rows of numbers representing the strength of radio signals detected from space. Most of the time those numbers were low, representing nothing more than background noise. But on one particular printout, there was a sequence of numbers that was clearly different, much higher than the surrounding data. Eamon grabbed a red pen and circled the sequence. Next to it, he wrote a single word, "Wow." He was genuinely surprised and excited. That spontaneous reaction is how the signal eventually received its famous name. It wasn't some official designation. It was one person's spontaneous reaction to seeing something unexpected. That human reaction, that sense of wonder and surprise is still part of astronomy today. When Tabby's star was discovered, the astronomers studying it were genuinely puzzled. They knew they were seeing something unusual. They worked hard to try to explain it. When conventional explanations didn't work, they had to consider unconventional ones, including the possibility of an alien megastructure. That suggestion was controversial. Many scientists criticized it. They thought it was irresponsible to mention aliens when there were potential natural explanations. But the scientists who proposed it weren't saying it definitely was aliens. They were saying they couldn't rule it out. And that's honest. When you have an observation you can't explain, you have to consider all possibilities, even the unlikely ones. This is what science looks like from the inside. It's not a smooth process where everyone agrees and everything makes sense. It's messy. People disagree. They debate. They argue about interpretations. They propose ideas that turn out to be wrong. But through all this mess, progress happens. Someone makes an observation. Others try to confirm it. People propose explanations. They test those explanations. Some explanations get ruled out. New observations are made. Gradually, understanding emerges. The scientists studying Zabilski's star have been puzzled for decades. They've proposed many explanations for the radioactive elements in its atmosphere. None of them quite work. But they keep trying. They keep making observations. They keep refining their ideas. That persistence is what drives science forward. Not giving up when things are confusing. Keeping at it. Trusting that eventually, with enough work, understanding will emerge. And sometimes it takes a long time. The cosmic microwave background was discovered in 1964. But it took decades of observations and analysis before scientists really understood what they were seeing. The detailed maps we have today, showing tiny temperature variations in the cosmic microwave background, came from satellites launched in the 1990s and the early 2000s. The CMB Cold Spot was first noticed in the early 2000s. Now it is 2025. Astronomers have been studying this anomaly for more than 20 years. We still do not fully understand it. But scientists have not given up. They continue observing. They continue thinking. They continue trying to understand what the data really means. That is what science requires: patience, persistence, and a willingness to live with uncertainty. These are not easy things. It is always more comfortable to have answers instead of questions. But the universe does not care about our comfort. It simply exists as it is, waiting for us to understand it. Our job is to figure it out. You might wonder why some of these mysteries have been around for years or even decades without being solved. The WOW signal was in 1977. That's almost 50 years ago. Why haven't we figured it out yet? There are several reasons. First, in many cases, we simply don't have enough data. The WOW signal lasted 72 seconds. We have one data point. One observation. It never repeated. That makes it incredibly difficult to study. Imagine trying to understand what an animal is based on seeing it once for 72 seconds. You might get some information. You could see its color, roughly its size, maybe how it moves. But you couldn't study its behavior. You couldn't see what it eats or where it lives or how it reproduces. One brief observation is limiting. That's the situation with the WOW signal. We have one observation. We can analyze it in detail, and scientists have done that. But there's only so much you can learn from a single data point. We need more observations, and so far we haven't gotten them. Tabby's star is a different situation. We have lots of data on it. We've been observing it continuously since it was discovered. We've watched it dim multiple times. We have observations from multiple telescopes in different wavelengths of light. But even with all that data, we're still not certain what's causing the dimming. The problem here isn't lack of data. It's that the phenomenon is complex. Multiple things might be happening. The dust theory explains some observations, but not all of them. We might need more detailed models or more observations in specific wavelengths or better theoretical understanding of how dust behaves around stars. For the Methuselah star, the main issue is measurement precision. Astronomers can measure many of the star's properties, its temperature, brightness, and chemical composition with very high accuracy. They can also estimate its distance from Earth reasonably well. However, when scientists combine all of this information to estimate the star's age, the result becomes difficult to explain. The problem is that the final age estimate depends on multiple measurements, and each of those measurements carries some level of uncertainty. When you combine multiple uncertain measurements, the uncertainties add up. Maybe one of our measurements is slightly off. Maybe our models of how stars evolve have a small error. These small errors could add up to make our age estimate too high. But figuring out which measurement is wrong or where our models need improvement is difficult. It requires very precise observations and very detailed models. And that takes time. Some mysteries take long to solve simply because they require technology we don't have yet. Before we had space telescopes, we couldn't observe many things clearly. Earth's atmosphere blocks certain wavelengths of light and distorts others. Space telescopes solve that problem. But space telescopes are expensive and take years to build. The James Webb Space Telescope was first proposed in the 1990s. It launched in 2021. That's decades from concept to reality. So, if solving a mystery requires a specific type of observation that only a new telescope can make, we might have to wait decades for that telescope to be built. Other mysteries take long because they require a theoretical breakthrough. Sometimes we have all the data we need, but we don't have the right conceptual framework to understand it. We need someone to think of a new idea, a new way of looking at the problem. These theoretical breakthroughs are unpredictable. They happen when someone has a creative insight. You can't schedule creativity. You can't say we'll have a breakthrough on Tuesday. It happens when it happens. The discovery of dark energy is a good example. In the 1990s, astronomers measured distant supernova to determine how fast the universe's expansion was slowing down. But they found the expansion was speeding up. This made no sense based on existing theory. It took time for the astronomical community to accept this result. Many scientists initially thought there must be an error in the measurements. But as more data came in from independent teams, it became clear the result was real. The expansion really was accelerating. But what could cause this? There was no explanation in existing physics. Scientists had to propose something new. They called it dark energy. They still don't know what it is. But at least now they have a name for it and can study it. That process took years. From the first confusing observations to the acceptance that something new was needed to the proposal of dark energy. Each step took time, as scientists gathered more data, debated interpretations, and developed new theoretical frameworks. The mysteries I have described tonight are all at different stages of this process. Some, like the wow signal, are still waiting for more data. Others, like Tabby's star, it already have a large amount of data, but require better theoretical explanations to fully understand what we are seeing. And some, like the Methuselah star, simply need more precise measurements. There are also mysteries like the CMB Cold Spot, which might eventually require entirely new theoretical ideas to explain. But all of these problems are actively being studied. Scientists are observing, measuring, thinking, and debating what the data means. Progress is happening, even if it sometimes moves slowly. And eventually many of these mysteries will be solved, although it is possible that not all of them will be solved within our lifetime. But someday these strange discoveries teach us something important about how science works. Science isn't about having all the answers. It's about honestly confronting what we don't know when we discover something we can't explain. The scientific response isn't to make up a story or ignore it. The response is to admit we don't know, to study it carefully, to consider multiple explanations, to gather more data, to think creatively about possible solutions. This is very different from other ways of knowing. In some belief systems, admitting you don't know something is seen as weakness. There's pressure to have answers, even if those answers aren't well supported. Science takes the opposite approach. Admitting you don't know is honest. It's the first step toward knowing. You can't solve a problem if you pretend it doesn't exist, or if you accept a convenient answer without evidence. The wow signal is a perfect example. We don't know what it was. Scientists have been honest about that for almost 50 years. They've proposed various possibilities. Natural radio sources, alien signals, terrestrial interference. But they admit none of these explanations is completely satisfying. That honesty is valuable. It means when we finally do figure out what the wow signal was, we'll know the explanation is based on solid evidence, not wishful thinking. The same is true for all these mysteries. Scientists are being honest about what they don't understand. That honesty is a strength, not a weakness. This approach also means science is self-correcting. When we make a mistake, when a theory turns out to be wrong, we change it. We update our understanding based on new evidence. History is full of examples. Scientists used to think the Earth was the center of the universe. Observations proved otherwise. Scientists used to think the universe was static. Observations showed it was expanding. Scientists used to think nothing could escape a black hole. Theoretical work by Stephen Hawking showed that black holes can evaporate through a quantum process. Each time the scientific community changed its views based on evidence, that's how it should work. Our understanding should evolve as we learn more. The mysteries I've described will likely lead to changes in our understanding. Maybe small changes, maybe large ones. But whatever we learn from them will make our picture of the universe more accurate. That's the goal. Not to protect cherished theories. Not to cling to ideas because they're comfortable or familiar. But to understand reality as it actually is. Even when reality is strange. Even when it contradicts our expectations. There's another important lesson from these mysteries. Technology matters. The tools we use to observe the universe determine what we can discover. The wow signal was detected because we built radio telescopes. Before radio astronomy existed, we had no way to detect signals like that. The whole phenomenon of cosmic radio sources was unknown until the mid-20th century. Tabby star was discovered because we built the Kepler Space Telescope specifically to monitor thousands of stars continuously. That capability didn't exist before. We couldn't keep track of that many stars at once. Kepler changed that. Odd radio circles were discovered because we built ASCAP, a new type of radio telescope in Australia. ASCAP can survey large areas of the sky quickly in radio wavelengths. It found these circles that previous telescopes had missed. Not because they weren't there, but because previous telescopes couldn't see them well. The cosmic microwave background was discovered by accident in 1964 when engineers were testing a new sensitive radio antenna. They found a persistent background noise coming from all directions. At first, they thought it was a problem with their equipment. Eventually, they realized they were detecting the afterglow of the Big Bang. But they needed that sensitive antenna to detect it. Each advance in technology opens new windows. Each new instrument reveals things that were hidden before. And we can be confident that future instruments will reveal things we haven't imagined yet. This is why funding for scientific instruments is so important. It's not just about satisfying curiosity, though that's valuable. 2. It's about expanding human knowledge. About discovering new phenomena that might have practical applications someday. Many technologies we use every day came from astronomy research. The sensors in digital cameras were developed for space telescopes. Wireless internet technology came from research on radio astronomy. Medical imaging techniques like CT scans use principles developed in X-ray astronomy. When we build new telescopes, we're not just learning about distant stars and galaxies. We're developing new technologies that often find uses in everyday life. The mysteries we discover with these telescopes drive further innovation as we try to solve them. So investing in astronomy isn't just about satisfying our curiosity about the universe, though that alone would be worthwhile. It's also an investment in technology and innovation that benefits everyone. There's something fascinating about how humans respond to mysteries. We're pattern-seeking creatures. Our brains are wired to look for explanations. When we encounter something we can't explain, it bothers us. It nags at us. We want to figure it out. That's why these cosmic mysteries are so compelling. They're real things that exist that we've observed and measured, but we can't explain them. That creates a kind of mental itch that we want to scratch. Think about the wow signal. For almost 50 years, people have been thinking about it. What was it? Where did it come from? Was it natural or artificial? These questions don't have clear answers. And that bothers us. We want to know. But here's something interesting. Living with uncertainty, with not knowing, is actually valuable. It keeps us humble. It reminds us that we don't have everything figured out. It prevents us from becoming too confident in our current understanding. Throughout history, humans have often been too confident. We thought we understood how the world worked, only to discover we were wrong. We thought the Earth was flat. We thought it was the center of the universe. We thought continents didn't move. We thought atoms were the smallest things. We were wrong about all of these. Mysteries like the ones I've described tonight remind us that we might still be wrong about important things. Our current understanding of the universe might be incomplete. There might be major phenomena or principles we haven't discovered yet. That's not a bad thing. It's actually exciting. It means there's still so much to learn. The universe still has secrets to reveal. We're not at the end of discovery. We're somewhere in the middle. Maybe even just at the beginning. When you think about it that way, mysteries aren't problems to be frustrated about. They're invitations. Invitations to explore, to discover, to learn. Each mystery is pointing us towards something we don't know yet. Something that once we understand it will expand our view of the cosmos. So, we've talked about a radio signal that appeared once and never again. A star that dims in ways no other star does. Giant radio circles around galaxies that we can't explain. Structures in the universe that are too large to exist according to theory. A void that's almost empty when it should be full of galaxies. A cold spot in the cosmic microwave background that's too cold to be a coincidence. A star with radioactive elements that should have decayed billions of years ago. An interstellar visitor with weird properties. Explosions that are brighter and faster than any known type of supernova. And a star that might be older than the universe. These are just some of the strange things we've discovered in space. And here's what's remarkable about them. They're all real. These aren't theories or speculation. These are actual observations. Things we've seen and measured. But more than that, they're all invitations. Invitations to understand the universe better. Invitations to think more carefully. Observe more precisely. And imagine new possibilities. Each mystery is the universe's way of telling us we don't know everything yet. And that's valuable. Science is about trying to explain observations. When we see something, we come up with hypotheses. We test those hypotheses. We build models. We make predictions. And when our predictions match observations, we feel confident that we understand what's going on. But sometimes observations don't match our predictions. Sometimes we see things we can't explain. That's when science gets really interesting. Every mystery I've described tonight is an opportunity. It's a chance to learn something new. Maybe our models are incomplete. Maybe there are processes in the universe we haven't discovered yet. Maybe physics works differently than we thought in certain situations. History shows that when observations don't match theory, it's usually the theory that needs updating. That's how science progresses. Newton's laws of motion worked great until we measured things moving close to the speed of light. Then we needed Einstein's relativity. Relativity works great until you get down to quantum scales. Then you need quantum mechanics. None of this means science is wrong. It means science is constantly refining itself. We're always improving our understanding. And every mystery is a clue pointing towards something we don't know yet. The wow signal might teach us about natural radio sources we haven't encountered. Or it might be evidence of something even more profound. Either way, it's a data point. Tabby's star is teaching us that stars can behave in ways we didn't anticipate. Whatever is dimming that star, natural or otherwise, it's expanding our understanding of what's possible. Odd radio circles are revealing structures in the universe we weren't aware of. They're showing us that galaxies can create or be associated with features that we're only now learning to see. The giant arc and big ring are challenging our assumptions about how uniform the universe is. They're suggesting that at the largest scales, things might be more complex than our models predicted. The Boötes Void and the CMB Cold Spot are pushing the limits of what we understand about large-scale structure formation in the universe. They test whether our understanding of gravity in the early universe is truly complete. Przybylski's star suggests that nuclear processes in stellar atmospheres might be more complex than we once believed. Or perhaps it is teaching us something about exotic forms of matter. Oumuamua opened our eyes to the reality that interstellar objects pass through our solar system from time to time. Astronomers are now watching carefully for more of them. Each new visitor could teach us something about planetary systems around other stars. Meanwhile, fast blue optical transients, or FBOTs, are revealing that the death of stars may occur in more varieties than we previously knew, expanding the catalogue of cosmic explosions. And the Methuselah star reminds us that our measurements and models always contain uncertainties. It keeps astronomers humble. Consider this: humans have been seriously studying the universe for only about 400 years. When Galileo Galilei first pointed a telescope at the sky in the early 1700s, modern observational astronomy truly began. 4 centuries may sound like a long time, but compared to the age of the universe, about 13.8 billion years, it is almost nothing. 400 years represents roughly 0.00003% of the universe's history. We have been observing the cosmos for only the tiniest fraction of its existence. And yet, during that short time, humanity has already discovered an astonishing amount about how the universe works. We've figured out what stars are, how they work, how they're born and die. We've discovered other galaxies. We've learned the universe is expanding. We've detected gravitational waves, black holes, neutron stars. We found thousands of exoplanets. We've mapped the cosmic web. We've observed the cosmic microwave background. All of this has happened in just 4 centuries. Now imagine what humanity might discover in the next 4 centuries. Or the next 4,000 years. Or even the next 4 million years. The universe is full of secrets. Some we have already uncovered, but many more remain hidden. Every telescope we build reveals new mysteries. And every new wavelength we observe shows us structures we never knew existed. Radio astronomy began in the 1930s. Before that, we had no idea the universe was filled with powerful radio sources. We could not see pulsars, quasars, or the cosmic microwave background. We did not know about odd radio circles, because we simply did not have the instruments capable of detecting them. Then came X-ray astronomy in the 1960s, followed by infrared astronomy, gamma-ray astronomy, and more recently, gravitational wave astronomy. Each of these developments opened a completely new window onto the universe, and each one revealed phenomena that scientists had never imagined before. So the question becomes, what will we discover with the next generation of telescopes? What wavelengths have we not yet explored? What observational techniques have we not yet developed? One thing is almost certain. In the next 50 years, astronomers will likely be studying phenomena that today would sound like science fiction. We'll have detected phenomena that we can't even conceive of right now. The universe is stranger than we know. It's probably stranger than we can know given our current level of technology and understanding. You might be wondering why any of this matters. Why should you care about strange radio signals or weird stars or giant structures in the distant universe? These things don't affect your daily life. You still have to go to work, pay bills, deal with everyday problems. But I think understanding the universe matters for a deeper reason. It tells us about our place in existence. It gives us perspective. We're living on a planet orbiting an ordinary star in an ordinary galaxy. We're part of a universe that's vast and old and full of wonders. Some of those wonders we understand. Many we don't. Knowing this changes how you see things. The problems that seem overwhelming, the disagreements that feel so important. They're all happening in the context of a cosmos that's mostly empty space and mysterious phenomena. That doesn't make your problems unimportant. Your life matters. Your experiences are real and valid. But there's something freeing about knowing that you're part of something much larger. Something strange and beautiful and full of mysteries. Every photon of light that hits your eye traveled from a star. Maybe a star in our galaxy. Maybe a star in another galaxy millions or billions of light years away. That light has been traveling through space for eons. It crossed unimaginable distances, and it ended its journey by hitting your retina, allowing you to see you're connected to the cosmos. The atoms in your body were forged in stars that died billions of years ago. You're made of stardust. That's not a poetic metaphor. It's literally true. The carbon, oxygen, nitrogen, iron in your body came from stars. And now you're living in a time when we can study the universe. We can build telescopes, collect data, analyze it, and learn about the cosmos. We can discover strange things that challenge our understanding. We can push the boundaries of knowledge. That's a privilege. For most of human history, people could only look up at the sky and wonder. They couldn't measure distances to stars or detect radio signals or observe the cosmic microwave background. We can. And every strange discovery we make is expanding what's possible to know. One of the hardest things about studying the universe is learning to live with questions that don't have answers yet. In our daily lives, we're used to getting answers quickly. If we don't know something, we can look it up online in seconds. We're used to immediate information. But the universe doesn't work that way. Some questions take decades to answer. Some take centuries. Some might never be answered. At least not in our lifetimes. And that's okay. That's part of what makes science fascinating. Think about the wow signal again. It's been almost 50 years. We still don't know what it was. That's frustrating. But it's also a reminder that the universe operates on its own timeline, not ours. We don't get to demand answers. We have to wait for the right observations, the right technology, the right ideas. This patience is actually valuable. It teaches us humility. It reminds us that we're not entitled to understanding everything immediately. The universe is under no obligation to make sense to us on our schedule. And while we wait for answers, we learn other things. We develop new technologies. We train new generations of scientists. We make observations that might not answer the original question, but reveal something else interesting. Science is full of accidental discoveries, things we find while we are actually looking for something else. The cosmic microwave background was discovered by accident. Pulsars were discovered by accident. Even penicillin was discovered by accident. So while scientists continue puzzling over mysteries like the WOW signal, Tabby's star, and many others, they are also carrying out other research, making new observations, and learning new things about the universe. The mysteries are important, but they're not the only thing we're doing. This is something non-scientists don't always understand. They sometimes think scientists are wasting time on unsolvable problems. Why spend decades studying something if you can't figure it out? Why not move on to easier questions? But the unsolvable problems often turn out to be solvable eventually. And even if they're not, the process of trying to solve them teaches us things, develops new methods, reveals unexpected phenomena. The search for dark matter hasn't found dark matter particles yet. Decades of searching. Billions of dollars spent. No definitive detection. Some people think this is a failure, but it's not. The experiments designed to detect dark matter have improved our understanding of particle physics, developed new detector technologies, and ruled out many hypotheses. Even failed searches teach us something. The same is true for these cosmic mysteries. Even if we never figure out what the WOW signal was, the search for it has advanced radio astronomy, developed better methods for analyzing signals, and taught us to think carefully about what evidence for extraterrestrial intelligence would look like. Tabby's star has taught us that stars are more complex than we thought, that there are behaviors we didn't anticipate, that we need better models of how dust behaves around stars. Even if we never definitively explain its dimming, we've learned valuable things in the attempt. Science isn't just about getting answers. It's about the process of asking good questions, developing methods to investigate them, and following where the evidence leads. The mysteries are part of that process. They're not obstacles. They're opportunities. We're nowhere near the end of discovery. Astronomy is a young science. We've barely scratched the surface. The universe is full of things we haven't found yet. Future telescopes will be more sensitive. They'll observe more of the sky more often in more wavelengths. They'll detect fainter signals, more distant objects. Each new observation has the potential to reveal something unexpected. Maybe we'll finally figure out what the WOW signal was. Maybe we'll detect another one. Maybe we'll find definitive evidence of intelligent life elsewhere in the universe. Or maybe we'll discover we're alone, which would be just as profound. Maybe we'll figure out what's dimming Tabby's star. Maybe we'll find more stars like it. Maybe we'll discover a whole new category of stellar phenomena. Maybe we'll understand odd radio circles. Maybe they'll teach us about galaxy evolution or supermassive black holes or something we haven't even thought of yet. Maybe we'll find more giant structures that challenge the cosmological principle. Maybe we will have to revise our understanding of how the universe is organized on the largest scales. Maybe we will finally solve the mystery of the CMB Cold Spot. Perhaps it will turn out to be caused by a supervoid after all. Or perhaps it will point to something even more exotic. Maybe we will eventually understand Przybylski's star. It could lead to discoveries in nuclear physics, or reveal something new about how stellar atmospheres and nuclear processes actually work. Maybe astronomers will detect more interstellar objects like Oumuamua. With better telescopes and faster observations, we will gather much more detailed data about them. Perhaps one will appear clearly artificial, or perhaps they will all turn out to be natural objects, teaching us about planetary systems around other stars. Maybe we will finally understand fast blue optical transients and discover that they are linked to black hole formation, neutron stars, or violent stellar collisions. And maybe we will eventually resolve the puzzle of the Methuselah star. Our models may improve. Our measurements may become more precise. And the tension in the data may disappear. Or perhaps we will uncover entirely new mysteries. Phenomena we cannot even imagine today, Puzzles that will challenge future generations of astronomers in the same way these mysteries challenge us now. That is the beauty of science. It is an ongoing process. The goal is not to have all the answers, but to keep asking better and deeper questions. We're trying to push the boundaries of what we know and understand. So tonight, when you go outside, take a moment to look up. Look at the stars. And think about the fact that some of those points of light are actually entire galaxies, collections of billions of stars, millions of light years away. Think about the fact that somewhere in that vast expanse, there is a star dimming in ways we don't understand. There is a void that is almost completely empty. There is a signal that appeared once and vanished. There is an interstellar object speeding silently through the darkness. There are explosions brighter than we thought possible. There are structures larger than our theories say should exist. The universe is strange. It is full of mysteries. And every mystery is an invitation to wonder, to question, to explore. We are incredibly fortunate to be alive at a time when we can study these things. When we have telescopes powerful enough to detect them, when we have the knowledge and technology to even recognize that they are strange. 400 years ago, none of this was possible. 400 years from now, we will understand far more than we do today. But right now, in this moment, we are on the frontier. We are pushing the boundaries. We are discovering strange things in space and trying to understand what they mean. And that is an extraordinary privilege. And it is happening right now. Not in some distant future. Not in some science fiction story. Right now in our lifetime. So when you look up at the night sky, remember this: you are looking at a universe full of wonders. Some we understand. Many we do not. And every strange thing we discover is a reminder that the cosmos is far more interesting than we ever imagined. The journey of discovery continues. The mysteries remain. And somewhere out there, in the vast darkness between the stars, there are strange things waiting to be found. Things that will puzzle us. Things that will challenge us. And ultimately, things that will teach us something new about the universe we live in. That is what makes astronomy so compelling. That is why scientists stay up late analyzing data, building models, trying to explain what, for now, remains unexplained. Because the universe is strange, and strange is wonderful. Let me leave you with one final thought. Every mystery we have explored tonight represents something real, something that exists out there. Right now, the wow signal happened. Tabby's star is dimming. Odd radio circles exist. These are not hypotheticals. They are observations. And that leads to something important. The universe does not care about our theories. It does not care about our models or our expectations. It simply behaves the way it does. And when we observe it carefully, we sometimes find things that surprise us. That is both humbling and exciting. Humbling, because it reminds us how much we still don't know. Exciting, because it means there is always more to discover. Science is not about having all the answers. It is about being honest about what we don't know. It is about looking at the evidence and admitting when we are puzzled. The scientists studying these strange phenomena are not discouraged by the lack of answers. They are motivated by it. Because every unsolved mystery is an opportunity to learn something deeper about how the universe works. Maybe some of these mysteries will be solved soon. Maybe others will remain unsolved for decades or even centuries. Maybe some will never be fully explained. But that's okay. The universe doesn't owe us easy answers. It is what it is. Our job is to observe it as carefully as we can. Measure it as precisely as we can. And try to understand it as best as we can. And when we can't explain something, we say so. We admit we don't know. We keep observing, keep measuring, keep thinking, because that's how progress happens. Not by pretending we understand everything, but by being honest about what we don't understand. The strangest things we've discovered in space are strange precisely because they don't fit our current understanding. They're outliers. They're anomalies. They're puzzles. But puzzles can be solved. Maybe not today. Maybe not tomorrow. But eventually, with enough observation and enough thought, we figure things out. That's the story of science, a story of mysteries gradually being solved, revealing a universe that is stranger and more wonderful than we imagined. So, the next time you hear about a strange discovery in space, don't think of it as a problem. Think of it as an opportunity to learn something new, an opportunity to expand our understanding. Because the universe is full of strange things. Some we've found, many more we haven't, and each one, when we discover it, teaches us something. That's the adventure of astronomy. That's why people dedicate their lives to studying the cosmos. Because out there, in the darkness between the stars, mysteries are waiting. Strange signals, dimming stars, giant circles, impassable structures, ancient voids, cold spots, radioactive elements that shouldn't exist, interstellar visitors, unexplained explosions, stars older than they should be. These are the things that keep astronomers awake at night, not because they're afraid, but because they're fascinated. And if you've made it this far, if you've listened to all of these strange stories, then maybe you're fascinated too. And that's a good thing. The universe deserves our fascination. It deserves our curiosity. It deserves our best efforts to understand it. Because the universe is strange wonderfully, beautifully strange. And that strangeness is exactly what makes it worth studying. Thank you for joining me on this journey through some of the strangest things we have discovered in space. If you enjoyed this exploration, a like or subscribe would really help the channel grow. And remember, the universe is full of mysteries. We have barely begun to understand it. There are strange things out there waiting to be discovered, things that will puzzle and amaze us. Things that may challenge everything we think we know. But that is not a problem. That is a promise. The universe is strange, and we are lucky to be here to witness it. Sleep well under the stars. And remember, somewhere out there, strange things are happening, things we do not yet understand. Things that one day might change everything we know about the cosmos. Good night.